we have a situation came up. We invented submarines, or we started to measure temperatures. And we invented these, we had these existing scales of numbers that started at 0, like 0 degrees Fahrenheit, which is very, very cold. But lo and behold, somebody came up with something that was colder than 0. What to do? How do we represent it being colder than 0? If 0 is already nothing, how do we go below nothing? Ooh, trouble. What do we do? How about we invent negative numbers? That's right, negative numbers. Numbers that start at -1 and they get bigger, but we put a little number, a little dash in front of them, then that means it's a whole different type of number. It means it's negative. And the bigger the number gets, actually the colder it gets, or the deeper it gets, or the more money I owe to the bank instead of I have the numbers as positive numbers in the bank. This is what negative numbers are used for. Very, very, very useful numbers. So what happened next? We put all these numbers together into a system of numbers called integers. This is negative numbers and positive numbers. This starts at 0 in the middle, and it can go positively to the right as many times as you want to, negatively to the left as many times as you want to. So, let's take a look at the big picture again. Notice that this big set of integers includes all the negative numbers. Look, the circle completely surrounds the negative numbers. If it's a negative number, it is also an integer. That is automatically true. Every negative number, well, every negative whole number, is an integer. It's not an integer if it's a fraction or a decimal or a percentage. We'll get to that. But negative numbers are the ones that are counting numbers, effectively, but with negative signs in front, are all included in integers. Likewise, all the whole numbers are included in integers. All the natural numbers are included in the set of integers. And all the zero number, the 1, is included in integers. Okay? But we're not done! Sorry. We're almost done with the standard, but we're not done with numbers and subsets of numbers altogether. Another problem came up. Okay, so now we have a scale that goes into negative numbers, and we have a scale that goes into positive numbers. But suddenly, we had situations came up where I needed numbers that went in between the numbers. Like, okay, so I got one glass of milk, and I got another glass of milk. What happens if I have another glass, but it's only half full? Or is it half empty? Or is it half full? Or is it half empty? I don't know. Anyway, the point is that it's between being a full glass, one glass, and being no glass. We didn't have a number system for that yet. Before that, all we could do was say 1, 2, 3, 4, or -1, -2, -3, -4. We couldn't say -1.5. We couldn't say 1.5. But if we invent a new number system, we can. What do we call that number system? We call it rational numbers. These are numbers that can be expressed as a fraction. What are fractions? They're numbers between the numbers. I know it's kind of a circular argument. What are rational numbers? They're numbers that can be fractions. And what are fractions? They're numbers that are rational numbers. But you get the concept. These are the numbers that we invented to say or to talk about things that were in between the other simple numbers. It's like when Grog and his friend Doug were in the cave. If one of them had broken a rock in half, they wouldn't have been able to talk about what just happened. They only knew 1, 2, 3, 4. They didn't know 1, 2.5, 3.5, or anything like that. But in science, it comes up all the time. All the time. The beaker is half full, or it's half empty, or it's 3/4, or it's 0.101, or it's 5/8 full. Fractions, they're very, very useful numbers. And they're included in this set of numbers, the rational numbers. Notice once again how this rational bubble surrounds all the other bubbles. Every integer can be said to be a rational number. Every non-integer rational number can be said to be a rational number. So all fractions that can be said simply with an integer at the top and the bottom, basically, or as a simple decimal, or a repeating decimal, those are all considered rational numbers. I'm going to move on. Because, sorry, another problem came up. We didn't invent these number systems because we want to drive students crazy. We really, really didn't. The only reason they had to invent different numbering systems is because reality bit us in the behind. Uh-oh. I just bit myself in the behind.
You should keep that in.
Excuse me for a second. But life is complicated, and using science and mathematics to understand life likewise had to be complicated. So when we got done getting all these numbers into play, we've got the fractions, we've got the negative numbers, we've got the positive numbers, we've got zero, we've got all that going for us, and we were pretty powerful. But something came along that threw another monkey wrench into the works. There were these weird special numbers called real numbers that were not rational. These numbers could not become fractions, they could not become integers, they couldn't become simple negative numbers. They were really, really weird. Basically, if you tried to turn them into a decimal, you would be dividing and dividing and dividing forever, and you would never come to the end of the problem. Likewise, that decimal would never repeat. It would just keep on going and going and coming up with weird, weird new numbers. Here's a couple of examples of numbers that have this weird special property. The square root of 2 was one of them. We can get in close on that. A very special number that's near and dear to my heart, pi, is an irrational number. They're also called transcendent numbers sometimes. This is a number that never ends and never repeats because it involves a circle, and yet we're asking how many straight line units are in that circle if you measure the outside of it. You can never be done. You can never really come up with an exact answer. You can get real close. But still needs a special set of numbers to include that number there and that number there, and the square root of 3, and basically the square root of any prime number is an irrational number. Prime numbers are a whole different issue. We'll get to that later. For now, it's time to practice and solidify what we've learned about these different numbering systems. So we have a little quiz.